Yeah, good morning my dear students. Today I am going to discuss the topic on applications of atomic absorption spectrometry. So when we discussed already about atomic absorption spectrometry, what are all the various applications? Because this atomic absorption spectrometry is limited to qualitative analysis. It will not reveal the chemical information of the sample. So mainly it is useful for quantitative analysis, exclusive technique for quantitative analysis for the determination of almost 70 elements, different type of elements present in the sample. Right. So when we do this multi-component analysis or single component analysis of elements in atomic absorption spectrometry, how will you perform this quantitative analysis? We are using two different methods. One is called external calibration method and the second one is called standard addition technique, which is also called as MSA calibration technique. MSA is shortly abbreviated as method of standard addition calibration. Now before going for this, you should know that in quantitative analysis, we are using two important parameters called LOD and LOQ. What is called LOD? LOD is the minimum detection limit, right? The limit of detection. That is a minimum concentration where you can able to detect the particular sample present, particular element present in the sample. That is called the limit of detection. So limit of detection LOD is equal to 3 into standard deviation of the blank solution, right? Which is operating under the same conditions as that of the sample. Similarly, if you want to calculate LOQ is nothing but limit of quantification. That is the minimum concentration which can be detected. Right? That is called the limit of quantification. So, limit of quantification is equal to 3 into LOD, or sometimes we call them as 10 into standard deviation of the blank solution, which is operating with the similar conditions as that of analysis of sample. Right? So LOQ is equal to 3 into LOD. Now if your range, suppose if your concentration is, if you are finding out the limit of detection is so much ppm for your sample and limit of quantification is so much ppm for your sample, if you find out, now if the range for some of the samples, if the range is between LOD and LOQ, in that case what we can identify, the identification is the element can be detected but not quantifiable. So that we call them as a semi-quantitative analysis, which we are doing in limit test for different elements like arsenic, limit test for chloride, sulfate, all these things. They are having the range between LOD and LOQ. They can be detected, but they cannot be quantified accurately, right? So this is the general basic things about the quantitative analysis of atomic absorption spectrometry. Now we are going to discuss about the external calibration method. When we talk about the external calibration method, I just took an example as a copper concentration in ppm. What I have to do is I have to prepare the standard solutions of copper in different concentrations, maybe 5 to 6 different concentrations, right? After preparing the concentrations of the copper, then I have to check the absorbance reading for individually for all the samples, right? So I put the copper concentration in ppm. This is basically the standard. And then what I am doing, I just go for plotting the absorbance. If you look at that, I am just plotting the absorbance here. Now, if I plot that with different concentrations, then I will get a linear straight line. I will be getting a linearity. So here, this is a calibration curve. And if you find out, if you are having an unknown sample, suppose if you have what concentrations, what type of solvents you are using for your standard sample, the same solvent, same methodology, we have to use it for the test solution also. So when we keep the test sample, only one test sample will be there. So if you take the absorbance reading for the test sample, whatever absorbance reading you are getting, you try to extrapolate in the standard graph. So where it is giving this thing, this will give the unknown sample concentration. This will try to produce the unknown sample concentration, right? So this is all about the graph present with the external calibration method. So we should remember that external calibration curves are prepared by the solutions of known concentration of the sample element. If copper means copper sulfate we are using, lead means lead nitrate we are using. High purity metals are dissolved in high purity acids. Generally when we use the metals, we are dissolving in high purity metals we are choosing and dissolving in high purity acids. They are used to make the stock standard solution, right? So the stock standard solution, how much concentration we are basically using? We are using either 1000 parts per million or 10,000 parts per million we are using as a stock standard solution. For atomic absorption spectrometry, the stock standard concentrations are 1000 ppm or 10,000 ppm as the element. And for most of the stock solutions, we just try to have the US NIST, National Institute of Standard Technology, using the materials, SRM materials we are using, that is called standard reference materials. They have the highest purity level, right? So standard reference materials if you are using, you will get accurate analysis, right? So we are using most of the elements. Instead of preparing the stock solutions every time, we directly procure the standard stocks available, solutions available with SRM, so that we are procuring and perform the things, right? So pure material is taken in different concentrations, at least 5 or 6 standard solutions we can take. Find out the absorbance of each by aspirated into the flame or furnace. You have to find out the absorbance of each by just aspirating into the flame or furnace. Prepare the unknown solution with the same solvent methodology. Whatever the optimum conditions you are using for preparing the standard, the same conditions using solvent methodology, you have to use it for test sample also. The linearity will be obtained in a low concentration, maybe from 0 to 10 ppm. And calibration blank 0 ppm standard prepared from deionized water and the same high purity nitric acid is used. Because I told already we dissolved in high purity acids. So that is the way we are preparing. One thing we should be keeping in mind, very important aspect, that is the sample and the standard. If you want to get the quantitative reliable data in a proper manner, so you have to maintain certain protocols commonly for sample and the standard. What are those protocols? You have to maintain the same solvent system for both the standard and the sample. Either it may be a water or alcohol or 5% nitric acid. And same matrix modifier we have to use it. Right? We have to use the same matrix modifier, whether we are using ammonium nitrate or magnesium nitrate or any other mixed modifier, whatever we are using, that should be used same matrix modifier in same concentration for both the standard and the sample solution. Same predominant anion at the same concentration we have to use it. For example, sulfate and chloride. And same type of flame. Flame also should not be changed. Whatever the fuel rich, that is fuel oxidant mixture we are using, air and acetylene, or the same graphite tube we are using, the same thing should be maintained for both the standard and the sample. And stable pressure in the flame gases during analysis, it should be also maintained in a similar manner. Absorbance measured at the same position in the flame or furnace. This is also very, very important. Right? The absorbance measured at the same position in the flame or furnace. Last but not the least, background correction carried out on each sample, blank and standard, using the same correction technique. If you use Zeeman correction technique, you have to use for both the standard and the sample with the same Zeeman correction technique. Right? So this is what we have to follow, the protocol for external calibration technique. Of course, it is a time tedious procedure, but accuracy is more and more reliable. Right? Because it is more time tedious. Why it is time tedious? Because we are preparing 5 to 6 different concentrations of the pure standard. Then after that we are keeping one concentration of the unknown solution. So totally 6 to 7 concentrations you have to prepare properly. Then you have to take 7 readings also. Then only you will get the accuracy here, right? So obviously it is a time taking process. The second important method what we are going to discuss is a standard addition technique, which we also call it as MSA calibration technique. What is called MSA? Method of Standard Addition Calibration. So why we are using this technique? For extremely complex sample matrices, if you have extremely complex sample matrices, it is not possible to make the external standards with a similar matrix. It is not at all feasible. Right? So in that conditions, when you have the extreme complex sample matrices, you always try to go for this standard addition technique. We also call it as MSA calibration technique, because it is an emergency based procedure. Very fastly you can see. There you have to, for example, if I give an example, if you want to go for kidney transplantation, I want to analyze the person's sodium concentration or the potassium concentration present in the renal tubular fluid. So in that case, I have to find out very fastly. Then only I can go for immediately kidney transplantation in a patient, right? So in that condition, I cannot go for using the first method where we have done with all the 6 to 7 concentrations, preparing in a slow manner and doing all these things. The patient will die definitely. So what we have to do, we have to do some procedure to find out the concentration of sodium or potassium in the kidney tubular fluid in a very urgent manner, right? But also in an accurate manner. How it is feasible? The only method, emergency procedure what we are using is standard addition technique. So this is basically an emergency based method. I just give an example here. The same copper can be determined in unknown sample solution, or sodium in renal tubular fluid, you can identify that, right? So what I am doing, I have to determine the concentration of sodium in unknown sample solution. In this case, what I am taking, I am taking the unknown sample solution, which may be containing your copper, maybe copper sample, any copper containing solution, right? So where it contains some amount of copper, right? So what I have to do that is a sample X. I just check the absorbance. I perform the blank also. Blank absorbance is around 0.1, right? This is the blank absorbance. It is around 0.1. Then I will be getting the corrected absorbance. The corrected absorbance is 0.3 minus 0.1, that is equal to 0.2. Okay. Now with the same container, what I am doing, I have to prepare because copper only you are going to evaluate. So what you have to do is that you have to choose some standard. The standard also same to that of your element. Suppose you are analyzing copper present in the unknown sample solution, then you have to make the pure standard solution of copper sulfate at a specified lesser concentration, right? So lesser concentration means a very minute concentration, 1 parts per million of the standard known copper sulfate we have to prepare it. Why we are using less concentration? Because if you are adding too much of concentration, that dilution and other aspects will be there, and it will affect the sample also, right? So that the absorbance should not vary too much, right? So what we are doing, we are adding a minute quantity, 1 ppm of standard known copper sulfate we are preparing, and minute quantity of this 1 ppm solution I am adding with the same container. So when I add this thing, what will happen? The container concentration will become x plus 1 ppm. Do you agree or not? So this x plus 1 ppm, now I have to check the absorbance reading for this thing in the flamer atomizer. So I am getting 0.5, blank is 0.1. So 0.5 minus 0.1, you will be getting 0.4, right? Now once only one, how many solutions you are doing? Only 2, that's all. One is your sample solution. With that you are adding the known quantity of the standard. Standard addition technique means a little known quantity of the same substance is added as a standard, and then check out the absorbance, right? So that is called spiking. We simply call it as spiking, right? Spiking, taking the sample and spiking with the standard. A known quantity of a little minute quantity we are spiking with the standard and check the absorbance variation, right? Now if you want to find out the concentration of the unknown solution, we are using a formula, that is absorbance of the test sample, corrected absorbance of the test sample divided by difference in absorbance into concentration of the standard added. It's a very simple formula. So what is the absorbance of the test sample? Test sample is X. So that is 0.2. Right? What is the difference in absorbance between the test sample and the 1 ppm added? The difference in absorbance will be again 0.4 minus 2, 0.2, that is equal to 0.2. Do you got my point? Into 1 ppm, that is the concentration of the standard added. How much concentration we have added into the sample? 1 ppm of copper sulfate. So into 1 ppm. So this gives the unknown concentration as 1 ppm, because 0.2 will get cancelled and you will be getting 1 ppm as the final concentration of the unknown sample solution. So if you want to plot the graph also, in the graph you will be getting the plot on the negative side, where they are intercepting on the x-axis. The negative side where they are intercepting on the x-axis, that is the value you will be getting as the final unknown concentration. So they will be coming as -1. If you take the modulus of -1, you will be getting 1 ppm. That is a unknown concentration of the test sample. Now this is all about the quantitative applications. Specific application of the drugs, how we are using this for a specific application of atomic absorption spectrometry in drug molecules. Some of the examples we are going to discuss. Palladium in carbonicillin sodium. If you look at that, the palladium present in the carbonicillin sodium at 248 nanometer. What is the concentration of palladium present in carbonicillin sodium? We can identify at 248 nanometer. Nickel present in prazosin hydrochloride. So prazosin hydrochloride is basically an antihypertensive alpha receptor antagonist. What is the quantity of nickel present? That is at 231 nanometer we are identifying. So the concentration of nickel should not be not more than 50 parts per million. This is the limited concentration we can allow the content of nickel present in prazosin hydrochloride. Beyond that, if it is present, the drug is not of valid use, right? We have to discard the drug sample. Silver present in cisplatin. Cisplatin is an anti-cancer agent at 328 nanometer. So the content or the quantity of the silver present in cisplatin will be not more than 250 parts per million. Similarly, iron present in ascorbic acid. This is one classical example. Ascorbic acid is a reducing agent, antioxidant. So the content of iron present in the ascorbic acid is very, very important, right? So we will be finding out at 248.3 nanometer, the concentration of iron should not cross not more than 2 ppm. Because iron, if it is present, what will happen? It will try to oxidize the sample, right? Iron is present, then they will try to oxidize the sample. So once they oxidize the sample, what will happen? They lose the reducing property as an antioxidant, right? So therefore, the content should be very, very limited. The content should not exceed more than 2 ppm. Similarly, copper, lead and zinc present in the activated charcoal can be estimated. Zinc in glucagon and insulin can be estimated, right? Similarly, cadmium and lead in zinc oxide. Zinc oxide is basically a calamine lotion. So where we are estimating the content of cadmium and lead, we can easily estimate, right? And phosphorus and zinc in the copper sulfate sample, we can estimate them. And lead in oxypronolol hydrochloride solution, that also we can estimate. That is oxypronolol hydrochloride for the treatment of glaucoma, right? And zinc present in sodium sulfate heptahydrate. So this also can be estimated by atomic absorption spectrometry. So this is all about the various applications of atomic absorption spectrometry in detailed manner. I hope you understand. Thank you, my dear students. Thank you very much.